Sairam and welcome to the next session. In this session we are going to discuss regarding linear equations. Let us begin this session with a prayer. Om Sai Ishwaraya Vidmahe Satyadevaya Dhimahi Tanna Sarva Prachodayat. Om Shanti Shanti Shanti. Okay, so till now we have taken a very close look at vectors. Right, we started off with vector addition, and we also defined what is called as scalar multiplication. And interestingly, the combination of these two led to what is called as linear combination. I think we spent quite an amount of time in understanding what are linear combinations of vectors, and after that we have moved into vectors aspects like magnitude and direction, and finally we have looked at dot product. Okay, so we are going to use all these knowledge now, because ultimately remember that we learn linear algebra for solving linear equations, is it not? Right? So we are going to try and use the knowledge that we have, and we will try and see how to solve two linear equations. Okay, so first let's understand what's a linear equation. It's a simple definition. We know that the degree of the variable does not cross 1. Okay, but that's not the only aspect. We can't, which means that we can't get terms like x square or x cube like that in linear equations. We will not be able to get those, right? Similarly, we talk about y square or y cube. No, they don't occur. The important fact is that we won't get even xy terms, right? So that's again a very important fact you have to keep in mind, that these are non-linear equations, right? But we are here looking at linear equations. Okay, now we understand what are linear equations. Let's take a look at two linear equations, and the moment this is given, we will get all our 8th standard knowledge to go ahead and solve this. So let's quickly solve this. That doesn't we can try the knowledge that we already have, and let's try and solve this. So let's add these two equations. So these two will get cancelled. We have 4x equal to 12, x equal to 3, right? So let's substitute it here. Therefore y should become 1, right? Okay, so we solve this equation, and we said that the solution we are getting, this is 3, 1. Okay, now we can also look at the equations in a geometric sense, right? So there are two variables, there are two equations and two variables. So let's try to plot these in R2, right? So we are trying to plot this in R2. Okay, let's first understand what does one equation in R2 actually stand for, right? And we know very well that this is nothing but an equation of a line in R2. And how do we plot the line? We typically in our earlier days, what we'll do is we'll pick up let's say a y value of 0, calculate the x, and then make the x 0, and then calculate the y, right? You can go ahead and try this, and then you will see that this is the line that we are talking about. So let me just write this here. So this is the line which is x minus 2y equal to 1. Okay, similarly try and attempt drawing a line for this, and you will get this line here. We see that this is the line which is 3x plus 2y equal to 11. Okay, and very interestingly, both of them meet exactly at 3, 1. Okay, and we know that that's the solution. Great, right? So this is typically the picture that we have been drawing in our mind. And remember this, that when we have a equation here in R2, one equation, and we try to plot this in R2, it forms a line in R2, right? So let's just keep this in mind. Now the same equations, I want to write it in a slightly different format, and that is where we are going to employ the knowledge that we are learning now, right? So let me rewrite these equations in another form, and you can check if this is correct, right? So could I write this as 1 and 3 in a column vector scalar multiple times x plus a -2 and a 2 with a scalar multiple times y is equal to another column vector which I am going to write it as 1 and 11, right? Would this be the same as these two equations, right? So if you take a deeper look, I'm sure you're going to appreciate and say that yes, it's indeed the same, right? Now you see something that's coming, right? We have a column vector, we have two column vectors, we have picked up the coefficients of these equations and we just put them in column vectors. So here are two column vectors in R2 and they are being multiplied by some values, x and y. Okay, here in this case we call them variables, and that is equal to a right hand side which is another column vector. Okay, what does this indicate to us? Have we seen this format somewhere, right? Does it not look like a linear combination? Linear combination of what? It is a linear combination of the column vectors 1 3 and -2 2, right? So if I call this as u and v vectors, we are basically trying to take a linear combination of two column vectors u and v, right? And what are we trying to solve in this equation? Okay, let's look at the right hand side. Let me give it a name here. Let me call it the b vector. Okay, we are saying that the linear combination of u and v produces b. Question is, what are those constants that I need, or what are the values that I need so that the linear combination produces this right hand side b vector? That's it. You see that the entire picture is now changing with our knowledge of linear algebra, right? With the basic idea, we have shifted from a picture that we would have learned earlier in our school days to something in linear algebra, and we are talking now about column vectors. Okay, so that's the picture that we are going to look at, and let us see what happens when we are attempting to interpret this geometrically. Okay, so let me show you this picture of these three vectors u, v and b. See this here. So let's mark out which is u, which is v, and which is the vector b, right? So which is u vector, which is 1 comma 3, right? So we can see here 1 comma 3, this must be our u vector, this must be the u vector. What's the v vector? Here it is -2 and 2, this must be the v vector, and the one in yellow is the 1 11, the longish one, and this must be the b vector. So let me just write it in yellow. This probably is the b vector. Great. Okay, now let's think about what is this meaning of this equation. How does this translate geometrically, right? We are saying find the numbers or scalars such that the linear combination of these vectors produce this, right? And we have understood in a geometric sense what is the meaning of the linear combination. Earlier when we looked at linear combinations, we had understood this in a geometric sense. So what it's going to mean is, how much do I walk on u and v? How much do I walk on u and v? I have to use only the directions u and v, and somehow I have to reach this vector b, right? How do I do that, right? So let's not worry about how to solve this, but the point is it possible to get here just by walking on u and v, right? Okay, now remember that when we talked about linear combinations, we were taking linear combinations of u and v, and we said that we can cover all vectors within it. Or when you want a vector somewhere here, we said that we can take the negation of this and then take the combination with the v and then try to get that vector, etc. Okay, now here what we are going to do is we are going to walk only on the directions of u and v, and somehow we have to reach b. Okay, so what we can do now is, since u is at least going towards in this direction of b, why don't we start walking on u, right? And let's do that multiple times and see what happens. So here is what I'm attempting. So I'm walking on u. Remember that for every one step we rise 3 steps, right? So when I walk on u twice, right? When I walk on u twice, that means that I would have taken 2 steps here, I would have risen by 6 steps here, so I have reached here, right? So suppose I say that I take 3 steps, so move 3 units on the x-axis, obviously I would have reached here, I would have risen to 9 units, right? So I would have reached this point 3, 9 here. Okay, now what's the benefit of reaching here? Now is it, I mean, at least we have got closer, right? We have got closer here, and what does this v vector give us? If you move in the negative direction of x by 2 units, it'll raise you by 2 units. Now let's see where we are. We are at 3, 9, and we have to rise 2 units from here, right? And if we move left by 2 units, right? So if I move left by 2 units, that's what it gives me. So let me just copy this vector and draw a vector parallel here, and let's see where we are reaching. And we see something interesting, right? So when I just walk parallel to v from here, which is effectively the v vector, I'm reaching this b, right? And what is this point? This is actually 1, 11. So from 3, 9, let's do a vector addition here. What was this? This is a -2, 2, right? So 3 minus 2 is a 1, and 9 plus 2 is 11, and yes, we got there to b. Fantastic. Okay, so what does this tell us? It tells us that walk on u 3 times and then walk on v 1 time, right? And it says therefore my x must be 3 and my y must be 1. Is the same solution that we looked at here, but what a different picture it creates in the column vectors, right? So since we are using column vectors and then trying to project the geometrical interpretation of it, we are going to term this as what is called as the column picture, right? So this we are going to call as the row picture. I'll explain you why we will call it a row picture a little while later, but this is the picture that we're interested in. Given any set of linear equations, we want to talk about the column picture and ask the same question. And what's the question we are asking? When we want to solve the linear system of linear equations, we are asking the question, what are the scalars? What are the scalars? So that my linear combination produces the right hand side vector, right? Now it may look like what's the big deal in the column picture, because after all it is also looking like another graph here. So is there any advantage of looking at it? Okay, my first advantage is that we are bringing linear algebra here and we are able to appreciate what is the meaning of solving versus what is the meaning of linear combinations. Okay, that is one. Second is, let me move to another higher dimension. Let me try and take you to say 3D and then see if there is any advantage of looking at the column picture. Okay, here are 3 equations. Now we are moved to R3. We have got 3 equations and in 3 variables. The first question, what does one equation in 3 variables represent in R3? Right? Let's think about this. Right? Does it represent a line? We had a similar question when we were in R2, and we answered that question saying that one equation in R2 in 2 variables actually represents a line. So let's look at this equation here. Let's say we have got x plus 2y plus 3z equal to 6. Okay. Now how do we try to draw this? If you want to put it in geometry, right? We have to fix 1 or 2 values for it and find the third, right? So one easy way to look at it would be, why don't we fix y and z to be 0 and I will get x to be 6, right? So one of the points that we can talk about is that whatever is that diagram, it has to pass through 6, 0, 0. Okay. Similarly, if I fix x and z to be 0, I'm going to get y to be 3, right? So this is going to be 0, 3, 0. Now what about z? So let me fix these two to be zeros and I will get z to be 2, right? So then I will have 0, 0, 2. Okay. So does it mean we are going to have a line that's going to pass through these 3 points? You can try, but it's going to be really impossible to draw a line that's going to connect these 3 points, right? So you can think about this, because we have these two one in the xy plane. Maybe you can look at a line here, but remember this is simply not on the xy plane, right? This is moving on to the z axis, and how are we even going to connect this line suddenly to a point in z axis, right? So that gives us an idea that this is not a line. That is interesting. Okay, that's not a line. Then what is it? Now, looking at this equation, if you want to find what are the degrees of freedom of it, right? So let me take you to a two variable equation. In the two variable equation, if I fix the x, we can find the y value, or if I fix the y, you can find the x value. Okay, so my degree of freedom is constrained to 1, because I choose one, other is automatically arrived at. Or if I fix x, you will have to, you don't have an option but to calculate a specific y value for it, right? So then my degree of freedom is just 1, and we saw what it represents, right? It was a line. Okay, let's get back here. Now let's see what happens here. If I fix x and y, I get the z value. Okay, but what did we say? We said that I can fix x and y, which means that I can choose whatever I want for x and y. Now, to be convenient, I think we were choosing it to be zeros, so that it's easy for us to calculate. But remember, I can simply randomly choose any two values for my x and y, and I can calculate my z, right? And therefore, what's the degree of freedom? It's the number of variables that you are able to choose freely, right? That's the freedom. That's my degree of freedom. And therefore, here I have got my degree of freedom to be 2, right? And when we are looking at these 3 points to be somehow connected, it is not a line, but it is going to be a plane, right? So one equation in R3 is representing a plane. In fact, you don't even have to have 3 variables. Even if I write one variable, I think it's going to be pretty easy to understand. Let's say that if we talk about x equal to 6, just think about what will happen in R3. What does this represent, right? It only says x equal to 6. That means that y and z can be any values. They could run till infinity, they could be 0, they could be negative, whatever it wants, right? All those points, right? Let me write one point and ask if this satisfies this, right? So if I say 6 minus 123 and minus 45 and ask, does this satisfy this equation? The answer is yes, it satisfies. So what does x equal to 6 represent in R3? It represents a plane that is fixed at x equal to 6, and in which direction? A plane that is running parallel to the YZ plane. A plane at x equal to 6. A plane at x equal to 6. And it's running, this plane is running parallel to the YZ plane. You will have to understand that this plane is actually cutting through, going into the screen and coming out towards us infinitely, going up and going down infinitely. It simply doesn't move on x because x is fixed. Whereas my y and z, I have got enough freedom, right? And therefore that's a plane in R3, right? Of course this is a R2 diagram, but I'm just trying to show what an equation means here. Similarly, you pick up 2 variables and then attempt, you will still get a plane. Take 3 variables and attempt, and we are still going to get a plane, right? Of course this plane may have certain constraints to it, but nevertheless one equation in R3 is only going to represent a plane. Okay, similarly the second equation represents another plane, the third equation could represent another plane, and therefore question is, what is going to be the solution to this? Okay, so we are going to have multiple planes intersecting with each other, right? We are going to have a plane and another plane intersecting each other, and when plane and a plane intersect each other, we are going to probably get a line, and then we are going to have the line intersect with another plane maybe, and it might produce a point, right? And finally the solution will we will arrive at a point. And it was similar in the R2, right? We picked up one equation, we know it represented a line, there is another line, the line intersects and we get a point here as a solution. Okay, it's going to be similar here, but only thing is the diagram will change now. It's no more line intersections, but it's going to be plane intersections. Two planes intersect probably to get a line, and that line may intersect the other plane, and we may land up finally at a point. Okay, let me attempt drawing this. Okay, now that we understand that these equations represent planes, I figured out the three coordinates, just like how we did for the first equation. I have also written down these points for the other two equations. Let me try and show you how the diagram is going to look like, at least for the first two planes. So remember at least the 2 points, I have a 6, 0, 0, 0, 3, 0, and there's a 2, 0, 0 and a 0.8 and 0, right? So let me try and show you the figure, right? So this is how complicated it's going to get when we try to draw the planes in R3. Okay, so I can at least mark a few points for you so that you'll be able to appreciate what's happening here. Let me put this point here. So this is the point which is 6, 0, 0, right? The other point we are talking about is 0, 3, 0, right? So here it is. So we have 0, 3, 0. Now how do we imagine this yellow plane is? Imagine a line here, and a huge cardboard sheet, right? So there is a tapering yellow color cardboard sheet, and this cardboard sheet is infinitely going up and down, and it's cutting the z-axis at this point. And that point is 0, sorry, let me write this here. So it is 0, 0, 2, right? So that's how you imagine this plane. Yeah, I'll show you the points again. We had 6, 0, 0, 0, 3, 0 and 0, 0, 2, right? That's the first plane. The second plane I'm trying to draw in orange. So you see those points there, it's 2, 0, 0, 0.8, that's also cutting it at 0, 0, 2, right? So the first point is 2, 0, 0, so that's here. This is our 2, 0, 0, and it's cutting the y-axis at 0.80. so this is the point 0. So let me put that in orange so that it will be clear. This is 2, 0, 0. This point is 0, 0.8 and 0. Okay, now imagine a line like this, that's the slope of that line, and imagine a cardboard in orange which is in the same slant, proceeding up and down and cutting the z-axis exactly at 0, 0, 2. It is something like saying the z-axis, this part of the z-axis is behind the orange cardboard, right? Whereas from this point it's piercing outside through the cardboard. Similarly, let me talk about the yellow plane. For the yellow plane, the z-axis is under this yellow plane from the origin till this point. After this, right, at this point it's piercing it's piercing the yellow plane and coming out from here, right? So that's how you imagine, and both these planes are infinitely going up and down, and only thing you have to understand is they have those slants, right? And those slants, they are intersecting here at this point, right? So the interesting thing is that these two planes we thought would intersect in a line, and that line, it is indeed a line, right? It's not definitely not a point here, but it is going to be a line. But that line is a little hard to imagine. You'll have to imagine two cardboards cutting each other, they cut each other, and that line is passing through 0, 0, 2, right? That's what we have got till now, right? It's going to get further complicated when we're going to draw the third plane, and let me attempt drawing that as well. So the points for the third plane is going to be 3, 0, 0 and 0 minus 2 by 3 and 0. So let's try and draw that. This is so the third one is in this green, and you have to imagine the plane again. So this is the point 3, 0, 0, and it actually cuts through the let me put that in blue. No, it's actually going in the negative y-axis, right? We said 0, minus 2 by 3 and 0 and 3 0 0. So imagine a line like that and draw this line infinitely, produce a plane that can taper so that it can cut from down under. It's going to cut 0 0 2 and then move up, right? Otherwise it's going to go deep down inside the screen, right? So it's coming from below, it's trying to cut 0 0 2 and then it rises up. So the change here is that the plane is under this part of the z-axis, and then it, after z-axis, it cuts the z-axis at this point and starts rising up, right? Starts rising up towards us out of the screen, right? So this is how hard it gets, and I don't think we should spend more time in looking at this. And let me write this down clearly so that you remember what kind of picture it is. This is the row picture, right? Keep the kind of complications that we have for this, and let me try and draw the column picture for you. So before we get to the column picture, let me write the equations as column vectors. This is what we learned in the R2. So let me try that in the R3 as well. Look at this, I've got the coefficients here 1 2 6, 2 5 minus 3 and 3 2 and 1, and keep the variables at the scalar constants and bring up a linear combination and put the right hand side vectors separately as another column vector. So here is the question we are asking: can we produce a linear combination of these three vectors which can give us the right hand side vector, which is 6 4 2, right? And something glaringly very visible for us here. Anyway, now let us try and draw the picture of these three vectors, right? Now I think I'm also going to draw the fourth one, including the right hand side vector. But in order to show you the 3D picture, now I'm trying to also draw cubes so that it or cuboids, so that it will give you kind of a 3D idea of where these vectors are lying, right? Otherwise, you know, if we remove the cuboids, the picture is going to be pretty simple. It's just going to have these three vectors and the fourth vector, which is the right hand side vector. So let me take you to that diagram. That's a row picture. Now look at this diagram, right? So I'm hoping that we are able to see 4 color boxes, right? So one long box here in blue, another small box in yellow, a longish one in green going behind, and an orange one that's coming out and large towards the x-axis, right? So it'd be interesting to see which are these vectors which are put in yellow. So let me write that down for you. So here are the 4 vectors that we identified, and you can now color match each one of them. Look at the 1 2 6, you know, yeah, it's just one unit in the x-axis, 2 units in the y-axis, but it comes quite far out in the z direction, or 6 units, right? So how should you imagine the vector? Imagine the vector from the origin as a line till this corner, right? So we are looking at the right and the top corner. That is the vector which is in blue, right? So that's our first vector which we wrote down there. So let me call it, say, vector 1. Okay, let me put that in blue itself so that you know, we don't have any confusion here. So be v1, right? The next vector we're looking at is 2 5 minus 3, and you color match this. You see here that, you know, we have moved 2 units in the x direction, 5 units up, but 3 units we went behind in the z, right? And therefore this is the point we're looking at. So you take a line from the origin to that point behind, and that's the 2 5 minus 3 vector, right? That's our v2 vector. Okay, let's move to 3 2 1. This is in yellow. 3 2 1, look at it. So 3 units in the x direction, 2 units up, and 1 towards us, towards this, I mean, out of the screen, 1 unit on z axis, and that's the smaller box here. We must imagine the point to be here, and imagine the vector to start from the origin going till here, this point. Okay, that's our v3. Okay, and the last vector, typically we name this vector as b, so let me give it the same name, b vector. 6 4 2, right? So 6 units x direction, 4 units in y, and coming out 2 units, and this is going to be the point where we have to imagine the vector starting from origin till this point. That's the b vector, right? Now question asked is, walk on V1, V2, V3 and can you reach 642, right? Now look at the line from the origin. It's very interesting that if we attempt to draw a line, it looks like we are going to almost pass through this guy and then reach here, is it not, right? So that's how it looks like, right? And that's it. That is the idea behind this picture. You will find that almost these two are overlapping. This is in this case, but the picture we are looking at, which is the column picture, becomes quite simple compared to the row picture we had, right? So please remove these boxes out of your mind, and we only look at these vectors, right? We only look at these vectors, right? So if I had only drawn the vectors, you wouldn't have been able to appreciate the three dimensions, and that's why I put the box. And now you can imagine the vectors, right? Now imagine this picture without the boxes. It's a pretty simple picture with those three vectors and the final right hand side B vector, asking the same question: can I walk on these three vectors and reach this B vector, right? Now the answer is pretty simple. So if we go and solve that using our regular equation solving methods, or if you look at it geometrically, in this case we are going to get the answer as 0, 0, 2. What it says is, you really don't have to walk in the direction of V1, you don't have to walk in the direction of V2. Simply take V3 and walk in its direction twice. Here it is twice, and you will reach B, right? And that's what it says. 2 times this is going to give us this, right? We got the answer in no time. Now the example is quite simple, because we could have got the answer even from here, right? So when we saw this 0, 0, 2 appearing in all three places, it was clear that that is probably the solution. Okay, but the agenda in this session is not to solve linear equations, but to frame, right? We are trying to find the picture for it, right? And therefore all that we are attempting in this session is to talk about what is the row picture of equations and what is the column picture of equations, right? When we move to 3D, you're able to appreciate that column pictures are quite simple compared to the row pictures. They're really hard to imagine, right? So with this idea, let us bring this session to a close. The summary of this session is quite simple. We have talked about row pictures and column pictures. Let us end this session with a prayer. Om Shanti Shanti Shanti.